Hi, my name is Matt Spinozzi, and in this video I'm going to be giving you an overview of the flavor science of distilled spirits. So a little bit about my background. I'm the owner of the Spirited Consultant and Functional Botanical Company. The Spirited Consultant is a consulting service for the beverage industry, and Functional Botanical Company is a non-alcoholic drinks company focusing on botanicals and non-alcoholic fermentations. I'm also a firefighter and EMT for Greenport Fire Department, and I have a Master's of Science in Brewing and Distilling from Heriot-Watt University. I'm currently a student at Johns Hopkins for a Master's in Biotechnology. I have a professional certificate in Cannabis Science and Medicine from University of Vermont's College of Medicine, and I have Bachelor's in History and Art History from Johns Hopkins. So before we delve into the flavor science, let's first define what we mean by distilled spirit. So we've got two definitions here. First one from Merriam-Webster's dictionary: an alcoholic liquor such as a brandy, whiskey, gin, rum, or arrack obtained by distillation from wine or other fermented fruit juice or plant juice or a starchy material such as various grains that has first been brewed. And then the federal government defines a distilled spirit as ethyl alcohol, hydrated oxide of ethyl, spirits of wine, whiskey, rum, gin, brandy, and other distilled spirits, including all dilutions and mixtures thereof for non-industrial use. The term distilled spirit shall not include mixtures containing wine bottled at 48 degrees of proof or less if the mixture contains more than 50% wine on a proof gallon basis. Fine. So I've got a simpler, less convoluted definition that I think is also a little more appropriate, particularly for discussing it from a flavor science perspective. And that is a solution consisting predominantly of ethanol and water, which has been obtained by the alcoholic fermentation of carbohydrates of agricultural origin and subsequent distillation of this fermented substrate to concentrated volatile compounds. And I've highlighted the parts here that I think are particularly important. So it's the solution consists predominantly of ethanol and water, in fact, almost entirely in most cases, and that the distillation is to concentrate volatile compounds. Now, from a composition perspective, a spirit is almost entirely ethanol and water, but the flavor comes from everything else, which in this case we're just going to refer to as congeners. So why does all the flavor come typically from less than 1% of the beverage? The answer to that is odor and flavor threshold values. Different compounds can have very different threshold values, and some can be detected at extremely low concentrations. For example, some individuals can detect trichloroanisole, cork taint, in the parts per trillion range, which is an absurdly low concentration. And there are even some compounds for which the human nose appears to be more sensitive than any current equipment we have, although this could be also due to the interactions between compounds that individually wouldn't trigger your sense of smell. It's also very, very important to recognize that threshold values can differ very significantly in different media. For example, ethanol versus water. This is one of the main reasons that dilution can have such a significant impact on the aroma of a spirit, because you are changing the solvent, or at least the concentration of the solvent, and so the threshold values of the different flavor active compounds in there will change accordingly. So we also need to differentiate between odor and flavor. Essentially, it's the difference between nose versus palate. Odor is only detected through the olfactory glands, so your sense of smell, whereas flavor incorporates not just your sense of smell, but also taste, mouthfeel, and the whole experience, essentially, of what you're consuming. So the best definition of flavor I could find, is better than anyone I could come up with, is from Van Gemmer, and its flavor is here defined as all perceptions based on the senses of odor and or taste and or the common chemical sense or other chemical senses when a food or drink is put into the mouth. When dealing with spirits, I find flavor threshold value to be much more useful than odor threshold value, and that's because it picks up on a lot more characteristics. For example, bitterness and acidity are detected by your taste buds, so they're included in flavor threshold value, but they're not there in odor threshold value. Same thing with astringency, tannins, and a lot of other sensations. Another important distinction is orthonasal versus retronasal olfaction, and this is essentially the two ways that you smell. And as you can see in this this diagram here, there are two pathways to get to the olfactory bulb. You've got the front door, orthonasal olfaction, which is going in through your nostrils and then coming back and hitting the olfactory organ. Or you can also go back through the back of the throat and up. And that's retronasal olfaction, and that's the main way that you detect flavor when you consume a food or beverage. It's coming up that back door, and that's also why if you have a bad cold or a sinus infection or something along those lines, and your sinuses are clogged, that you don't really detect much when you consume food, because that retronasal olfactory pathway is obstructed. So you're really just left with those 5 key tastes that you get in your mouth, and all the nuance is what's going to come from that olfactory bulb is severely toned down. So as I said, with taste, there are 5 key tastes, and that's independent of odor, and that's what you're going to get in your mouth, whether or not you have that pathway, that olfactory pathway blocked. So the 5 key tastes are sweet, acidic, bitter, savory, and salty. Acidic is sometimes called sour, and savory is sometimes called umami. There are other potential taste being something that strictly defined as something that you can detect with your taste buds. And the other proposed ones are metallic, fatty, starchy, and kokumi. Kokumi is sometimes described as hearty. It's a Japanese word. Of these, I'm pretty skeptical on 3 of the 4. The only one that I actually think that I personally get is metallic, and there's also a very good evolutionary reason why we would be able to detect metallic tastes with our taste buds, and that's because blood is metallic. There's a lot of iron in blood, so it makes sense from that perspective. And personally, I do think I get metallic as a taste independent of all other flavor sensations. Also incorporated in flavor is mouthfeel. So this is independent of both taste and odor, and this is pretty much almost everything else that's going to be captured in there. So viscosity, piquancy is spiciness, cooling, like menthol from mint, the actual temperature of the food. Some food is anesthetic, it causes numbing, like cloves does, and irritation or burn. Ethanol, for example, is a good example of that. Alcohol itself causes irritation of tissue, and that's where that burning sensation when you have a high proof spirit comes, and that's independent of both taste and aroma, but it's also integral to the overall flavor experience. So now, what are the sources of these flavor compounds? Well, so first of all, you have the substrate. That's what your beverage is fundamentally made from. So in terms of whiskey, that's your grain. In Calvados, that would be your apples, the sugar cane or sugarcane byproduct in rum, etc. And then you have the substrate processing. So malting of the grain would be an example of that. How you process your apples in a Calvados. If you're smoking your malt, that has a major impact on the flavor of the final product. For example, fermentation is also a huge source of flavor compounds. This is where you're going to get a lot of flavor production, particularly of compounds like esters, is going to be in your fermentation. Distillation. We don't usually think of distillation so much as a source of flavor compounds, but more of a stage in which we're separating out different compounds. But you also do have compounds flavor compounds created during distillation, because it's a hot environment. You have chemical reactions going on during distillation. Maturation. Maturation contributes flavor compounds in two main ways. There's the extraction from the wood, or whatever vessel it's being matured in. Some are inert. Wood is definitely not inert. And then there is just the chemical reactions that occur during maturation of the different compounds that are in the spirit reacting with one another. Dilution. Dilution actually can contribute flavor compounds, because you're not usually diluting with just pure H2O. There's other stuff in that water. There is, oftentimes minerals in there, etc. So if you've got, for example, calcium carbonate in your water, that's going to have an impact on not only by adding that calcium carbonate directly is that having a flavor impact, but it's changing the pH, and that'll have an impact on the overall flavor of the whiskey and the chemical, or of the spirit and the chemical reactions that are going on in there. Additives. Obviously, people put things in spirit sometimes, whether it's caramel coloring or boisé or propylene glycol or sugar. There's a lot of stuff that gets added after the fact, and these can definitely impact the flavor of a spirit. And filtration. Filtration is, unless you screw something up or have a dirty filter, shouldn't be a source of flavor compounds, but is you're removing certain flavor compounds. So that also has a flavor impact on the spirit, obviously. So what actually is distillation? Fundamentally, distillation is the separation of compounds based on their volatility. The more volatile a compound is, the more readily it vaporizes. And so the more volatile compounds are present in higher proportions in the vapor at the beginning of the run, because they've volatilized more readily. As the run proceeds, there's a lower concentration or a lower availability of these compounds within the pot, talking in pot distillation and batch distillation, and so as that concentration decreases, while the temperature of the still is gradually increasing, because you have the lower volatility compounds predominating in there, this encourages progressively less volatile compounds to vaporize. And this is the premise of how you make your cut points as a distiller. So fundamentally, you have your heads, your hearts, and your tails. And some distillers might take multiple cuts or get a little more complicated than that, but fundamentally, you get your heads, your hearts, your tails. Your heads is the start of the run. That's the most volatile compounds, and you're going to try and concentrate some of the nasty compounds you don't want that have high volatility into your heads, and that gets set aside and either gets recycled or used for something else or discarded. And then you've got your hearts. That's actually your product stream. That comes in the middle of the run. And then you've got your tails, where you've got some very low volatility compounds, or relatively low volatility compounds, that also don't taste as nice. And those are, again, going to get either discarded or recycled or put into another use. Reflux is also crucial in distillation. And reflux is the return of condensed vapors back to the pot. And it's essentially a factor of surface area and temperature. So a higher amount of reflux means you have more vapors that have come off that liquid. They've had a phase change from liquid to gas, but then they've turned back into a liquid, recondensed, and fallen back into the pot. And so and they're going to end up getting redistilled. And so the more reflux you have a higher degree of rectification. And that's because, for the same reason that the more volatile compounds vaporize more readily, the less volatile compounds condense more readily. So it's not even. So say that vapor coming off say the liquid in the pot is, say, 8% alcohol. That vapor coming off right off the liquid might be 30% alcohol. But if you've got a lot of reflux, the water is going to condense preferentially or more readily than the ethanol. So as it goes up and you get more and more condensation, that ethanol is going to be enriched. So by the time you get to the breakpoint where we go to the condenser, you might have something that's 50%, 60% alcohol, and because of that reflux. Now, high reflux is neither categorically good nor bad, but it does change the way the distillation runs, and it's a mechanism by which the distiller can influence his distillate. And there are things that you can do as a distiller when you're running stills to influence the reflux. Some stills, there's a lot of things you can do. Like if you have a dephlegmator, you can play around with the condenser temperature. If you've got plates in a column, you can adjust the settings on those. But even if you're just running a good old-fashioned pot still, like a good old alembic, there are things you can do to play around with the reflux and change the character of your distillate. So here we have the two basic types of still. You have a pot still on the left and a column still on the right. So this is also the difference between batch and continuous distillation. So in a pot still, you charge the still with your, say, 1,000 gallons of whiskey wash goes into the still. You heat it up. It goes through the run, and you've got your distillate, and then which is the vapors that you've recondensed, and then you've got what's left in the pot, your pot ale, your stillage, whatever you want to call it, and then you empty that out, and you do it all over again. You're doing it in batches. A column still operates differently, so you're constantly feeding in new wash, and it's going through a series of trays which are giving additional reflux, and then you've got your product stream out, and you've got pulls usually for your heads and your tails, or your fusel oils, feints, whatever you want to call them. Sometimes you'll have multiple pulls, and you've got your stillage or your spent wash coming out as well. And that operates continuously. It's a much more efficient way of distillation. Continuous distillation is from a sheer throughput and output standpoint, but the character of the spirit is quite different. Usually, it's used to produce lighter, more highly rectified spirits. That is almost always the case, but not always. You do have spirits such as Armagnac, where they are produced on a different something that operates fundamentally the same, a continuous column still, but with a pretty low degree of rectification. So there's always exceptions. Now, I've spoken a lot about volatile compounds, so I want to explain that a little more, the difference between volatile and non-volatile. So here, when we talk about flavor compounds, we can categorize them as either volatile or non-volatile. And in this context, when I say volatile, I mean compounds that can vaporize in the still, or evaporate in the still at atmospheric pressure, while non-volatile compounds do not. They won't vaporize within the still. So new make distillate should only contain volatile compounds unless there has been aerosolization, where particles that are not vapor just get carried up on those convection currents, or if there's a boil over. Normally we'd call that the still puking. So that's if you've ever boiled pasta and you're not paying attention and it starts to foam up and it foams over the edge of the pot. It's the same basic thing can happen in a still, where as you're boiling that wash, it foams up, and if you're not careful, you're not paying attention, that foam comes all the way up and goes over through into the neck of the still and gets into your condenser, and that is not good. And you have to do you should be doing a deep clean of your system after that, discarding or at least redistilling what comes off of that, and it's a big headache. And so that is a way that you will get non-volatile compounds in your distillate, but you don't want that to occur. And similarly, you can get them if the condenser is not clean, especially if you had a boil over, you didn't clean it on subsequent runs, you can have non-volatile residue contaminate your product stream. In distilled spirits, the non-volatile compounds are often very important for flavor in matured spirits, and those are generally going to originate in the wood during maturation, or they're added from another source after distillation. For example, in absinthe, where you have a maceration of botanicals, that you will be also extracting non-volatile compounds. Or as I mentioned before, if you put caramel coloring in or boisé, sweetener, those are non-volatile. Those are generally going to be non-volatile compounds that make their way into the distilled spirit. So there's some key compound categories for distilled spirits. So you have alcohols, esters, terpenes and terpenoids, aldehydes, diketones, phenolic compounds, carboxylic acids, sulfur compounds, and saccharides. We're going to discuss each of those in some more detail now. But first, I just want to give a quick note on flavor chemistry, and that is that the overall character of a spirit is not simply a matter of containing certain compounds at certain levels, and these can be reduced to a chart or a fancy graph or spreadsheet, graphic, whatever. These are all very useful aids in most cases, but it's really important to stress that the balance and interaction of all these compounds is what really makes the flavor, and the flavor of any spirit or beverage or food can't just simply be reduced to a chart or graph, no matter how pretty or fancy it looks. It's only capturing a small facet of that whole experience. So it's useful, but it doesn't give the whole picture. So first up, let's talk about alcohols. Now, obviously, the most important alcohol is ethanol. This is beverage alcohol, also known as ethyl alcohol. It is 2 carbons with a hydroxyl group. Now, you'll often hear the term higher alcohols or fusel oils. These all mean the same thing, and it's any alcohol with more than 2 carbons. That's considered a higher alcohol. These all have lower volatilities than ethanol, which you'll often see abbreviated as ETOH, and so they come later in the run. More towards the tails, and they're almost entirely a product of fermentation, and they can be formed either from amino acids via the catabolic pathway or from sugars via the anabolic pathway. And here we just have a chart showing alcohols and their corresponding amino acids and aldehydes. So alcohols can typically be oxidized into aldehydes, for example, ethanol to acetaldehyde, which can then further be oxidized into a carboxylic acid, in this case, acetic acid or ethanoic acid. Another alcohol that's very important is methanol. This is the only alcohol that is a smaller molecule than ethanol. It's basically the same structure, except instead of those 2 carbons, it's got 1. Methyl means 1 in organic chemistry. So because it's smaller and because of that structure, it is a lighter molecule, higher volatility. So it'll congregate generally towards the beginning of the run, but its physical properties are very similar to that of ethanol, so it's quite difficult to fully separate out methanol from ethanol. Methanol is quite toxic, a hell of a lot more toxic than ethanol, and methanol toxicity can cause blindness and even death. As a note, there's a strong correlation between the pectin content of a substrate and the methanol content of the spirit. So the more pectin you have in a substrate, all things being equal, the more methanol content you are likely to generate during your fermentation. Another note on methanol is you might often hear people say, that moonshine has a lot of methanol in it, or that's why you go blind. The reason that people go blind from drinking illicit booze is generally not because there's enough in the fermentation. It's actually quite difficult from a normal any type of beverage substrate that you'd normally be using to create enough methanol to really do that much damage. But ethanol that's sold for industrial purposes, because ethanol has a lot of industrial uses, by law has to be denatured in some way to make it unsuitable for beverage consumption. That's what the federal government mandates. And so the most common way of doing this is to add methanol to it, making it poisonous. And then unscrupulous people will either try and fail to separate out the methanol from the ethanol, or they'll just try and stretch their run by adding methylated spirits, which don't have the excise tax that beverage alcohol does, and that's where the methanol will get into moonshine. It's not actually from the production of the spirit. It's just unscrupulous people adding stuff, and then the government mandating that poison be put into products that it doesn't need to be put into. Carboxylic acids. So this is another category of very important flavor compound. The one that most people will be familiar with is acetic acid, also known as ethanoic acid. This is the main acid in vinegar. This accounts for the majority of volatile acidity in most spirits. It can be formed in fermentation or by the oxidation of ethanol, or it can come from barrels, particularly if those barrels weren't properly maintained, particularly old wine barrels with a bacterial infection in them, like Acetobacter can have a lot of acetic acid in there, and that's generally going to be considered a flaw in the spirit. Now, bacterial action during fermentation can create a lot of different acids, not just acetic acid. Lactic acid is a very common acid, particularly in whiskey fermentations and rum fermentations, and certain types of brandy fermentations, where you're going to have a lot of types of lactic acid bacteria that are crucial for getting the flavor characteristics that you're looking for. One of the most extreme examples that many people might be familiar with of bacteria creating acids as part of the fermentation is in a dundered rum. This is dundered means using a type of spontaneously fermented backset or sour mash in rum that's typical of some high ester Jamaican rums. These carboxylic acids are important, not necessarily because they themselves come over into the final product, into the spirit, although some do, but their main flavor contribution is in that they react with alcohols to form esters. And esters, as we're going to discuss in a minute, are a very flavor active class of molecules. They're responsible for a lot of flavors, and that's where a lot of the flavor in spirits will come from, is esters. Now, most of the acids in spirits are going to be straight chain monocarboxylic acids, up to 18 carbons. But sometimes you can find some branched chain acids that are coming from usually bacteria, or sometimes from some weird chemistry in the maturation from the barrels. Here we just have a chart that's showing the average carboxylic acid content of some spirits. This is just for illustration. I don't actually have a lot of faith in these numbers. They're very just a very loose approximation, and without a whole lot of qualifications here. But just to give you an idea of sort of what you're looking at, and you can see that Grand Rhum rum, like rum agricole, would have a very high acid content. So we were talking about esters and how alcohols react with carboxylic acids, and you get esters. Now, the acid doesn't actually have to be a carboxylic acid, but when we're talking distilled spirits, your esters are generally going to be the reaction between a carboxylic acid and a alcohol. And it's basically when you have an alcohol reacting with an acid, and you have the elimination of a water molecule. So here you can see what happens when acetic acid, also known as ethanoic acid, that's, as we said, the main acid, or the acid that is vinegar. Typical distilled vinegar is just 5% acetic acid and 95% water. And when acetic acid reacts with ethanol, and you have the elimination of a water molecule, you get ethyl ethanoate, also known as ethyl acetate, and that is going to have at low concentrations a slightly sweet, like pear drop aroma, and then at higher concentrations, it gets sort of this sort of powdery, candyish aroma, and then when you get a little higher, it gets quite solventy, and smells like nail polish because it's used as a solvent in a lot of industrial applications, including sometimes nail polish. Should be differentiated from acetone, which has a similar smell but is nail polish remover, and has a different set of physical properties and chemical properties. Esters are very flavor active, as we said, and they're responsible for the aromas of a lot of foods, particularly fruits. So a good example of this is isoamyl acetate. That is an ester that really just smells like ripe bananas, and that's because it's the main ester produced by ripe bananas. If anybody has had Laffy Taffy, like the banana flavor, the main chemical used to flavor that is just isoamyl acetate. Another example, particularly if you're Irish or British, would be banoffee, which is like a banana toffee, and again, that has a lot of isoamyl acetate in it. Certain beers have a lot of isoamyl acetate in them because yeast can also produce isoamyl acetate. So it's characteristic of some Hefeweizens, for example, and that's how it gets into spirits. Is that generally the yeast can produce these esters, and some yeast will produce a lot of isoamyl acetate. There's a lot of other esters that can be produced that will give very important characteristic flavors to spirits. In pretty much all spirits, the dominant ester is going to be ethyl acetate, the one we were just discussing. That you get because ethanol is your dominant alcohol, and acetic acid is your dominant acid. So it follows the reason that your dominant ester is going to be what happens when those two react. But esters are widely used in also in like flavors and fragrances, and it's very important that all aspects of production can impact ester content, even though they're mostly produced during fermentations. Lactones are often referred to separately from esters, but they're actually a type of ester. They're cyclical esters formed by hydroxy acids, and they're very important in the flavor of a spirit, particularly for the flavor of oak-aged beverages. They're a lot of the characteristic aromas of oak are lactones, but they're also in dairy, as you might have guessed from the name, and particularly stone fruit can tend to have lactones that are important for their flavor. And they can also be produced by yeast, so that's mainly through oxidative pathways. So the yeast are going to be producing lactones when they have in the presence of oxygen, whereas your typical fermentations for spirits are going to be anaerobic, not in the presence of oxygen, because yeast won't produce ethanol in its oxidative pathways. And here we just have a chart from the same source showing the average ester content for different types of spirits. And you can take this with many grains of salt, but it does give you a general idea where you're going to see that, for example, in the different rums on the right, you can have a very broad range of ester content, and Jamaican rum tends to have very high ester content, and so does Grand Arome Agricole, versus something from, say, Barbados, which you're gonna might have a lighter rum. And similarly, you can have a very broad range over different brandies, and the whiskeys I would ignore some of those numbers because they don't make a lot of sense. But American whiskey does tend to have, for example, a higher ethyl acetate content than a lot of other whiskeys. And aldehydes is another very important class of flavor molecule. These are mostly formed during fermentation, and there is a strong correlation between aldehydes and their corresponding keto acids. And the nutrient composition of fermentation is going to have a big impact on aldehyde formation. Aldehydes can also be formed during maturation through the oxidation of alcohol. Certain wood phenols are thought to catalyze this reaction during maturation of wines and spirits, and particularly, as we mentioned before, ethanol to acetaldehyde. Now, because acetaldehyde is formed by the oxidation of ethanol, it is going to be the dominant aldehyde in most cases, and usually constitutes up to 90% of the total aldehyde content of whiskey, brandy, and rum. It's often used as representative of the total aldehyde content of a spirit. And there are some other aldehydes that you might find in pretty significant quantities. And for example, furfural is a product of Maillard reactions, and you also have phenolic aldehydes. And another potential important source of aldehydes is particularly in like gin distillation. Certain botanicals will have a very high aldehyde content. Like citral is an important aldehyde that you're going to get in certain citrus and lemongrass, lemon balm. That is quite aromatic. Aldehydes are also reactive compounds, and they can react with alcohols to form acetyls. And during maturation, this will reduce free aldehyde content. And aldehydes tend to be pretty sharp and in flavor, so that's part of the rounding out of a spirit. Now, usually most of this softening occurs pretty early in the maturation, and this is why that spirits even, or not the only reason, but part of the reason that even spirits after 2 weeks after coming off the still, even if they're just held in an inert vessel like glass or a plastic tote, they actually round out quite a bit, and a lot of that has to do with the softening of just some of those aldehydes. And it's not going to be complete, and it's also a reversible reaction, and it is heavily influenced by the not only the concentration of aldehydes and alcohol, but also the pH. Here again, same source. You can just get an idea of the rough aldehyde content of some different types of spirits. So diketones, the major one is diacetyl, and this is going to have a butterscotch aroma. It is the main compound used to flavor artificial butter or movie theater popcorn, and it is formed in fermentation. It can be formed by both yeast and bacteria. Next up, we have terpenes and terpenoids. Terpenes are hydrocarbons built of isoprene units, and terpenoids are their oxygenated derivatives. These are strong-smelling compounds that are found in many plant materials, particularly essential oils. In fact, if you go into your spice cabinets and take a look at all the botanicals and spices you have in there, the dominant aroma compounds in pretty much every single one of those are going to be terpenes. I'm going to use the term terpenes to refer also to terpenoids for simplicity here. Similarly, if you have the essential oil of a plant, that's generally going to be predominantly terpenes. So in a spirit, terpenes are generally going to originate in raw materials. They can also esterify and hydrolyze, particularly from the heat of distillation. Not all of them are very thermally stable. And they can also be biosynthesized by microbes, but that's not generally where you're going to get them in the case of distilled spirits. Because they're really important for the aroma of botanicals, they are responsible for most of the flavor of gin. So juniper, for example, is characterized by its terpenes like alpha-pinene, beta-pinene, limonene, terpenine, terpenoline. Coriander, same thing, is characterized mainly by the terpene. Its aroma is characterized by its terpenes, and that's true for most of the botanicals in gin. Terpenes are also plentiful in grapes, so in brandies you're also going to have some significant flavor contribution from terpenes. And there's also a lot of research currently being done on the bioactivity of a lot of terpenes, and especially with cannabis and how the terpene content of cannabis impacts how the cannabis hits you, and how it interacts with how they interact with the cannabinoids and something known as the entourage effect. We also have phenolic compounds. So simple phenols or monophenols, they the phenolic aroma that the people are going to be most familiar with would be the smoky flavor of a peated whiskey, and this is usually indicated by the total phenol content in parts per million (ppm). This can be a bit misleading, but oftentimes you'll see the number is actually the phenolic parts per million of the malted barley that's used. So lightly peated will be 1 to 5 ppm milligrams per liter is the same as ppm. Intermediately peated will be 5 to 15, and then heavily peated will be 15 to 50, and then anything above that is just super heavily peated. But the phenols are fairly low volatility compounds, and most of the phenolic content in the malt doesn't actually make it into the spirit. So the actual phenolic content of the spirit will be much lower than that of the substrate. And that also is going to be heavily influenced by other aspects of the production method, particularly distillation. So take, for example, two Islay whiskeys, Caol and Lagavulin. Their malt is pretty much identical. They're both owned by Diageo. They get their malt from the same sources, and it's to essentially the same spec, but their production methods are very different, and there's other differences as well, but fundamentally Caol takes a much higher cut than Lagavulin does, and consequently, although the ppm going in is roughly the same, the ppm coming out is much higher in Lagavulin spirit than it is in Caol spirit. And now phenols are also antioxidants, so they will oxidize during maturation. So that overall phenolic character will soften over time during maturation. They're not only found in peated whiskeys; they can be found in anything that's sort of smoky. They have savory flavors. On their own, they're actually quite unpleasant. But they're a nice condiment, if you will. Just like there's a lot of things you don't really want to be eating pure, but in very small amounts. They're nice. I mean, like food without salt can be quite bland, but you put a little salt in there, and it's nice. But you put a ton of salt in there, it doesn't taste good. Same thing with black pepper. A little black pepper is nice, but you don't really want to be eating predominantly black pepper. So examples of phenols would be phenol, creosols, and glycols. And incidentally, the picture over on the right, Pradella Maltings, is where a lot of the malt for Caol and Lagavulin comes from. We also have polyphenolic compounds. So tannins are an important example of polyphenolic compounds. These are going to be non-volatile compounds, and so they're going to be generally acquired from the wood during maturation. These are astringent compounds, and the reason they're astringent, that refers to that sort of, if you have, say, a tannic red wine, that mouthfeel you get, it's almost like there's like something coating your tongue that's sandpapery. Well, there is actually something coating your tongue, and that's because tannins will precipitate out proteins in your saliva and form a little coating on the surfaces in your mouth, and that's what you're feeling. They're generally acquired from the wood during maturation because, as I said, they are non-volatile, and they're divided into two basic categories: hydrolyzable and Non-hydrolyzable tannins. Hydrolyzable tannins, examples of those would be elagitannins and gallotannins, and these are generally going to come from oak, as the name might suggest. And then you have non-hydrolyzable tannins. These, for example, you're going to get from the skins in red wine, and they're going to be often pigmented, and you're going to get some of the color. A lot of the colors coming from that. They are antioxidants, and they will change chemically over time due to oxidation. And that's actually a really big part of maturation of both spirits and wine, particularly red wine, is the oxidation of tannins, polyphenolic compounds. So if you take a whiskey, for example, at first, when you start maturing that whiskey, particularly if it's a bourbon and it's in a new oak cask, it's going to pull a lot of stuff out of the wood, and it's going to pull a lot of tannins out of the wood. These tannins are going to be very harsh, and they're going to soften over time as they oxidize. And that's the similar thing with red wine, and that's one of the reasons that red wines are decanted. You don't want to, if a wine is actually at its peak maturation, you don't want to decant that because it's already oxidized the right amount, and if you decant it, you're going to over oxidize it. But with a lot of wine, these big tannic red wines, you're drinking them before they have had the perfect amount of oxidation of the tannins. So by decanting it and aerating it, you're introducing a bunch of oxygen, and that's going to help to give that last bit of oxidation that these tannins need to soften and round out. And we can't forget about sulfur compounds. Most sulfur compounds have very, very low flavor threshold values. They often get a bad name because they're responsible for some pretty nasty aromas, but in low concentrations they can give some really pleasant flavor notes and really add to the complexity of a spirit. So for example, you can get like meaty, stewy, smoky, rancio, even like lemony notes or grapefruit notes from some sulfur compounds. In higher concentrations, they give pretty unpleasant aromas, burnt rubber, rotten egg, cabbage, just general rotten notes. Most sulfur in a spirit is going to originate from the degradation of amino acids, particularly when those amino acids are metabolized by the yeast, and it forms hydrogen sulfide and some other sulfur compounds. Stressed yeasts are going to, all things being equal, are going to produce more of this, particularly if they are fan deficient, free amino nitrogen, meaning basically yeast assimilable nitrogen. So they're going to start scavenging for nitrogen from amino acids, liberating sulfur. Some of the common sulfur compounds that you're going to find in spirits would be some stuff like DMS, dimethyl sulfide, DMDS, dimethyl disulfide, and dimethyl trisulfide, DMTS. The DMS, for example, in high amounts will give sort of these cooked cabbage, sort of rotteny aromas, but in low amounts is really a pleasant aroma to give meaty notes, and just make a spirit more savory. Thiols, aka mercaptans, for example, if you ever smell, if you have a propane leak or a gas leak, people say, "Oh, I smell gas." You don't actually smell the propane. Propane doesn't have a or methane, natural gas, doesn't have an aroma. And what they do is they add methyl mercaptan in very small amounts, because it's got such a low odor threshold value, into that gas, so that if there is a leak, you can smell it really easily. So you have a couple other classes of sulfur compounds in there as well. It's also really important to note that many of these classes of sulfur compound will react with the copper in the still. This is why one of the reasons why copper is such an important material to have in the still, and why why high quality stills tend to always be made of copper over stainless steel if we're talking metal stills. So the copper will react with some of these sulfur compounds and help either strip out unwanted sulfur compounds and or break them down into more pleasant compounds. So for example, copper will break up dimethyl trisulfide, and some of that will turn into copper salts and stay on the copper, but you'll also actually have some of that coming through the still as dimethyl sulfide instead of dimethyl trisulfide, and the dimethyl sulfide is a more pleasant compound than dimethyl trisulfide. This reaction, pretty much all chemical reactions, will happen at a higher rate at higher temperatures. So all things being equal, if you run your condenser hotter, particularly if you have like a worm tub and you have a where the spirit first enters the condenser, if you have a really pronounced temperature gradient throughout the condenser, A, you're cooling more efficiently, and B, you're going to get a little more reaction with the with that copper. Copper can also, as a side note on copper, can also catalyze certain esterification reactions and some other reactions. So copper is the metal you want to see in your still. Maillard reactions. So Maillard reactions are reactions between amino acids and reducing sugars, and these form a lot of flavor active molecules, sometimes referred to as non-enzymatic browning. They can produce certain sulfur compounds, which are also important for flavors, such as furfural compounds. Maillard reactions are generally associated with nutty, cereal, and sulfurous notes. Examples of Maillard reactions would be toasting bread, searing a steak, stuff like that. Those are all Maillard reactions. Important to note that caramelization is not a Maillard reaction. That is a different type of reaction. That is a pyrolysis reaction, which is basically thermal degradation. So it doesn't require an amino acid, but they often co-occur. So often, if you're in a situation where you have Maillard reactions, you might also get some pyrolysis reactions or caramelization. They are caused by heat, so higher distillation temperatures are associated with increased Maillard reactions. So as a result, direct fired stills tend to have hot spots, particularly if they are solids in, where you have which can be very prone to scorching, but if done well, you have hot spots, and these don't quite get to the point of scorching, but those are going to have a lot more Maillard reactions. So direct fired stills tend to have the highest amount of Maillard reactions. Here are the references. If you have any questions or are having difficulty obtaining something from one of these sources or others, feel free to shoot me a message and I will try and help you out. Or if you just have any questions about the content of this lecture or related content. Here's my contact info. Feel free to send me an email and or just leave a comment below. Cheers.